Okay, so we finished off the second video by outlining two different tests, kind of this overall omnibus test where we test is at least one of the predictors significant, and also the t-test, which tests the individual predictors. So let's just have a look. We had this LM.treat rate model that we built like in the last video. And let's get some more information about it. And we can do this by using the summary command. Now you see we have the coefficients as before. So we have these estimates. This is our beta 0 and this is our beta 1. We have the standard error. So this is in the test I showed you before, the standard error beta. These are the standard errors. Now you remember the t-value was the the beta divided by the standard error. And then we get the p-value here. Now, we don't really need to know is the intercept actually significant or not. So we usually ignore this. But we want to know the significance for the tweets per hour. And you can see here that it's highly significant as my p-value is very, very small. And you see there's kind of the levels of significance here as with the other tests we've done. And the 3 stars means we're less than 0.001. So we're going to reject the null hypothesis that this beta is equal to 0. And we're going to say that it's significant. We also have, remember, we have the variance accounted for, the 0.8242. And the adjusted R-squared, which accounts for the number of predictors. Now, we actually have in this last line, and be careful because people always mess this up in the exam, this is basically this omnibus test I showed you before, the F test for all the predictors. You see, we have the degrees of freedom. We only have like 1 degree of freedom here because this is kind of K. This is the actual. This is a kind of we only have like 1 predictor, and we have 21 error degrees of freedom, and this is our p-value. So again, it's incredibly significant, and you can see it's pretty much the same value here, and it should be because, you know, we're testing the same thing. We only have 1 predictor and we're testing if at least 1 predictor is significant. So we're doing really the same as the t-test. Now let's think a little bit about the regression and some of the assumptions of the regression. So let's stick with our little example. Of kind of the tweet rate per hour. So we have the X, we have the tweet rate per hour, and on the Y, we have the opening weekend revenue. And let's just draw some of these residuals here. And let's draw our regression line. And let's just put in a few little residuals here. So these are just the errors. And just kind of as a little bit of fun, let's just say this one. We've got a movie here with a high tweet rate per hour but low revenue. I'm going to say that this is the movie Snakes on a Plane. If you remember that from a few years back, it got a load of social media buzz. Because, hey, everyone wants to see a movie about snakes on a plane. But nobody actually went to saw it because people don't actually want to see a movie about snakes on a plane. So, again, this model is not perfect. So what are my assumptions of this model? 1, the mean error is equal to 0. So we'd say the expectation of epsilon equals 0. And that kind of makes sense from our least squares procedure in that we should have, the line should kind of bisect, it should be really in the middle. Number 2, the variance is equal to sigma squared. And it should be constant. And the constant error, we actually call it homoskedastic, as opposed to heteroskedastic. And what that means is the magnitude of the errors should not really increase. Now we'll find in our example it actually does. That can be an issue with something like this. Because imagine I'm trying to predict revenue for the new Avatar. And it's, you know, it's going to be hundreds of millions. I might be 50 million out. If I'm trying to predict a small art house film with a revenue of 5 million, I might be 500,000 out. So in our example, that's not exactly true. And the error distribution is normal. So kind of at any given point, if we have a distribution of errors, of what the errors might be, the errors should have this kind of normal distribution. And number 4 is the errors should be independent. And what does this mean? Well, we'll do it up here. So say we had a regression and say we had a lot of errors down here and then we suddenly shot up and had errors up here. Here the error is kind of related to the previous error, so the errors are not independent. Okay, so now we're going to go back and show how we test these things in... Okay, so we have our LM, and what we can do is we can actually... It comes with some built-in plots for diagnosing some of these problems. Now we're going to run this. We're going to run the par equals mf row. And if you remember, this is just splitting our screen into 4, our graphic screen. So we're doing it by 2 rows and 2 columns. Now then we do the 4 plots. And we can test for a few things. And again, watch out for this. This is always on the exam. So what we have here in the top left is we have our kind of fitted values, our y-hats, and then we have the errors. Now, homoskedastic errors, the average error, you know, beyond 0, should be relatively constant. You see this isn't happening here. We've got very small errors here, bigger errors here, and huge errors here. And in fact, this second plot basically does the square root of the residual, so they're all on the kind of the same side. And you can see here, this kind of gives the, you know, just the magnitude, whether it's positive or negative. And you can see you have small values down here, and you have bigger values up here. So these 2 plots basically show you the same thing. Now the normal QQ plot, this basically shows if we are close to normal. This basically, we have a normal distribution, and this is the equivalent of the normal distribution. And if every point is on here, then our errors are normal. And you can see here that this point is off normal, this point is off normal, this point is off normal, and this point is off normal. Now, I mean, all this does is it's kind of what we expect given the normal distribution and what we actually get. And again, we're a little bit off it. Our tails are a little bit different. But to be honest, I've never seen a perfect normal QQ plot in all my life. So everybody always says check the normal QQ plot, but it's never absolutely perfect. Now, what this is residuals versus leverage. And what this does is it's trying to find overly influential observations. Now, let me go back and give you a quick example of this. to say we have a regression. We're on red, so we'll stick with red. Oh, let's go blue. Let's mix it up. And we have all these guys here. These are all my X's. So we're going to draw a regression line. It goes something like, probably goes something like this. Let's just remove those couple of observations here. But yeah, we got this regression line that kind of goes almost like this, but it's in quite a small area of X. Now we add a new observation, this guy here, and suddenly, because of the least squares, this is a huge error. So this error outweighs all these other errors. So my new regression line is going to look like this. So this guy has high leverage. So this guy, you know, just one observation, it might have been a badly collected observation, or it may be something strange in your data, has completely messed up my regression. So what this does, this plot, is it shows our residuals, and it actually plots this idea of leverage. And we use something called Cook's distance. Now, if I'm not going to go into the math, these videos are long enough, but you can look it up. Now, if Cook's distance is over 1, this means we have this highly influential value. And recall, these movies were ordered, so the first movie was the highest revenue, and the second was the second highest. And you see, this is a highly influential, and number 2 is almost highly influential. So we have 2 levels. Over 1, it's very influential and very high leverage, and between 0.5 and 1, it kind of has this relatively moderate leverage. So we found out that we're not doing very well on, you know, our errors. We find, okay, they're not particularly normal, and they're pretty heteros. They're not homoscedastic. So what's one way of doing this? We kind of then put it on the log scale. That's a standard way of trying to remove some of this scale and distance effect. And let's just run a model where we log the y and we log the x. So this is our new model. And you can see here, we have exactly the same model, but we're now logging it. And so we have the log y, log revenue, is the log tweet rate per hour. We can see it's still incredibly significant here. Now let's do the same plots as we had before. And we can see we don't quite have this kind of heteroscedasticity anymore. If we look particularly in the second plot, most of our residuals are kind of in the same range. It's not this situation where we have very small errors and they're very big errors. They're all around the same magnitude. We also don't have anything. We have one that's kind of close to the 0.5, but we don't have as many influential observations. And we don't have, and again, I said we never see this perfectly normal, but we don't maybe have 1 or 2 quite as extreme here on the QQ plot. Okay, so now we're kind of going to move on, and we're going to examine how we do regression on qualitative variables. So firstly, we're going to load, now this is from the textbook. This chapter, I'd actually recommend you read the textbook. This is the free online textbook, because it goes into what I talk about, but it goes into it in more detail and a slightly higher level. And what we're going to do is we're going to take a data set from ISLR, and we're going to call it, it's called credit. So a lot of packages in R include data sets, including this one. And let's just have a look what's in credit. So we have the ID of the customer, which actually isn't very useful to us, so we're going to get rid of it in a minute. Kind of income, limit, credit rating, number of cards they have, the age of the education. So this is kind of a standard financial data set. Gender, student, married, ethnicity, and how much they have in their balance. Now this is a very simple simulated data set, but it does show some interesting things. So yeah, let's just get rid of the first column. Now first, we're going to plot a scatter plot with credit var. And what we do is, this is actually just plotting the scatter plot. We're using the pairs command. And it just plots the scatter plot of each item with each item. Now, a lot of these guys, if this scatter plot is not particularly useful, we could have actually done without them, because these are kind of the autonomous variables. But if you look here, income and credit rating and credit limit are pretty closely related. And in fact, you'll see that, which will be important later, credit limit and credit rating have an almost perfect relationship. Obviously, you've set the credit limit directly based on the credit rating. So these are all kind of quite highly correlated. Now, I'm going to show you a second kind of scatter plot. This is in the G-Galley package. This has a function called GG pairs. So it's like a GG plot version of this. And this could actually take a little bit of time. It's almost there. Almost there. Here we go. So what does this show us that the others don't? Well, we actually shows us for each variable with itself, it actually just shows the distribution of the variable. And for categorical variables, if it's a categorical variable with a continuous variable, it just shows us a box plot, as we've been doing the first few weeks. So this is income via gender, income via whether they're a student or not, income whether they're married, and income via ethnic group. And you can see here, if we have two categorical variables, it just shows us the frequencies of the different categorical variables. So we have gender and student. So this will be student no, student yes, the two different gender variables. Same for married here. It just kind of shows the size of the boxes, shows the relative number of items in what would be a contingency table. So let's build a very simple model here. And first, let's actually just do a little summary of the data set. And let's look at these. I'm afraid we're a little bit out of date on gender. I guess a modern survey we would have a third gender, but this is the data set. So we have gender, male, female, whether a student or not, whether they're married or not, and we've got the balance here. Now we're going to build regression models, and this is going to be, and also we have, again, this is a very simple data set. So we have three ethnicities. We have African American, Asian, and Caucasian in the data set. So let's build a linear model where we have balance as a dependent variable and married as independent variable. And we'll just do the summary in kind of one command. So you see here, and I'll explain what this is in a minute, we have yes, they're married, and this is not significant. Now, we're going to do the same for ethnicity. And again, we can look at the levels of ethnicity because it's a factor variable. So if African American, Asian, Caucasian, and we can do a summary here. And again, we're not significant, but we see we actually have two categories here, Asian and Caucasian, but we're missing African American. Now, why is that? And you see, this is not really particularly, there's no information in this at all. The regression, the individuals are not significant. The regression is not significant, a p-value of 0.959, and the R-squared is virtually nothing. But let's just think a little bit about how we set up these variables. Okay, so in the married example, we had some variable, let's just say x1, and that's going to be 0 if not married, and 1 if married. Makes sense. It's a binary variable, and we have two states, yes or no. So we basically have two categories, not married and married. So we have two categories, one variable. So let's just now go to the ethnic group, and we have two variables. X1 is 0 if Asian, and 1 sorry. Okay, sorry, yeah, it was 1 if 0 if not Asian, and 1 if Asian. And x2 is 0 if not Caucasian, and 1 if Caucasian. And here we have the three categories, and we have two variables. Now, what does this mean? Well, the third variable is what we call kind of a dummy variable, in that if we had all three of these categories, we'd be able to infer the third category from the other two categories, and then the regression would be over-specified. And basically what we'd have is if we have if we say had three variables, then we'd have this kind of what we call collinearity and have perfect collinearity. And the technical reason why this is a problem, and again it's a little bit beyond this course, is when we do regression we invert a matrix. And if we have this kind of collinearity and what we call linear dependence, in that one of the independent variables can be calculated from the others, then that just basically crashes the regression. So that's not a good thing. Now, how does this actually relate to practice? Well, let's kind of go back to this. So here, and I actually put this math in the notes. So here, we have these kind of two dummy variables for Asian and for Caucasian. And, this is not significant, so you probably wouldn't do this regression anyway. But if you had, for example, this estimate here, this is the estimate for the dummy category, which is African American. And then this is the x1, the Asian. So if we're Asian, our x1 equals 1. And if we're African American or Caucasian, this is equal to 0. And so for Asian, then we subtract 18.69. And if we're Caucasian, then again, the x2 equals 1, and for this for ethnicity is x2 equals 0. So for Caucasian, we would actually subtract 12.5. So let's just kind of go back here. And let's kind of write out our regression. So y equals beta 0 plus beta 1 x1 plus beta 2 x2. So this is my kind of Asian variable. And this was the Caucasian. Now, let's just kind of put this x1 and x2. And this would be kind of African American, Asian, Caucasian. Here, x1 and x2 would both be 0. For Asian, this would be 1 and this would be 0. And Caucasian, this would be 0 and this would be 1. So say, for example, if looking at what we had with the regression, this is kind of the base variable. So this was, I can't remember what exactly that was. That was 531. This was minus 18.69. And this was minus 12.5. And so for African American, it's going to be 531. For Asian, x1 is 1, so beta 1 times x1 is the value of minus 18.69, so it's 531 minus 18.69. And for Caucasian, this guy is 0, so we don't worry about this, but this guy is 1, so we incorporate beta 2, and it's minus 12.5. So again, I actually lay all that out in the notes, so just make sure you check that out. Now, what we talked about here was perfect collinearity. But we can actually have a situation where we have two independent variables that are very highly correlated. So we have two that are kind of highly correlated. And so how do we work? And this can cause problems. This can cause linear dependence and an unstable regression. So what we do is we basically have a regression. So we have for each I, so for each of our predictors, it's just saying for each of the I equals 1 to k, we do a regression where xi is the dependent variable, and basically we regress it on all the other predictors. So everything except xi. So we basically run it on all the other predictors. And then we find an R squared for the regression. And basically we have the variance inflation factor, which is 1 minus 1 over Ri squared. So if one of my predictors is highly correlated to the other predictors, then R squared is going to be high. This is going to be, value down there is going to be very small, and this variance inflation factor is going to be very high. And we also have 1 over this is the tolerance. And so generally, VIF greater than 10 is a problem. It means we're highly collinear, and greater than 5, we maybe want to look at things a little bit. And again, that means a tolerance of less than 0.1 and a tolerance of less than 0.2. So let's go back to the R. So let's build a credit model. And basically, we're trying to predict balance based on everything in the data set. This is why we got rid of the first column. The dot means everything else. And let's do a summary. And you can see here we have income and the credit limit are highly predictive. Rating is a little bit. Cards is highly. Age a little bit. Education, not really. Gender, no. Student, yes, obviously married, and the ethnic variables are not significant. And you see it's a pretty good regression. You know, the R squared is 0.9551. You're unlikely to get such a good R squared in a realistic situation. Now we're going to use the OLSRR package, and this has a function called OLSVIF-TOL, which calculates the variance inflation factor. And you can see here that for credit limit and credit rating, we have these huge VIFs. And this is because of this correlation between rating and limit. They're almost pretty much the same variable. So we don't really want them in the same regression, as they make things unstable. So let's now do another regression. And we're doing the same regression as before, but this time you can actually specify minus in regression as well as plus. This is basically everything minus the rating. And you see you get the regression, we don't get the rating. And this is a much more stable regression. Do we pass the test? Yeah, you can see all these variance inflation factors are now less than 10 and certainly less than 5 as well. But now that we decided that, you know, this model's okay, but it's got a lot of junk in it that really isn't predicting. You know, we're not... education and gender and ethnic group aren't really doing anything in this model. So we're actually going to remove all those guys from the data. And we're going to do a third model, which is kind of our final model. And this is the thing with regression. It's a bit of an art. So here we have our final model. Now, sometimes, as we'll find, you can have something that's kind of maybe not quite significant or mildly significant that still has predictive power. And we'll talk about that in a minute. So now let's just check the function again. And you can see again, we're still less than 10. Okay, so the final thing we're going to do is we're going to look at a data set that we actually kind of look at in the homework, and this is called the Armours housing data set. So we're going to read this in. And let's have a look at it. And it's quite a complicated data set. We have, somewhere here, we have a selling price of houses, which is our dependent variable. And we have lots of information. Maybe this is, it's because we have too many columns here. So somewhere here, we have the sale price of a house. These are house prices in Armours, Iowa, and we have a huge amount of information about the houses. So we literally, let's just kind of have an str on it. We literally have lots and lots of variables. So how on earth do I begin to build a regression model for this? It's like, man, it's just too complicated. I don't know what's important. So let's kind of create a couple of models. The first we're going to do, we're just going to say the sale price is based on the lot area and the living area. So we have the lot area and the living area, both significant. Bigger houses cost more money. being more land costs more money. And our R squared is about 0.5. So we were planning about 50% of the variation. Now let's add the neighborhood. And suddenly we're up to 0.75. So it plays 75% of the variation in the Y. Now, why is this? What's happening here? Remember we said we had dummy variables. So what R has done is it has designated the neighborhood as a base neighborhood. And I think it's just done the one with the alphabetically the first. And it's created dummy variables for every other single neighborhood. So you can see here, for example, that Green Hill is an expensive neighborhood. So being in Green Hill adds this to the power of 4. So it adds like, nearly $8,000 to the sale price. So it's at $80,000. Yeah, $80,000 to the sale price. But being in this neighborhood here has all IDOTRR, whatever that is, it has almost the opposite effect of the sale price. So you can see the neighborhood, location in real estate, neighborhood is very important. What other variables can we do? So let's just remove any kind of NAs from the data. So this is just a way of, maybe I went a bit too fancy here, but if we have some NAs in the data, then we're going to remove this data from the Armis housing. And let's just see what we've got left with. So this is what's remaining. We still have quite a lot of predictors. We still have a complicated model. So we're going to do what we do is stepwise regression. We're going to specify a base model. Now the base model is just the intercept. And if we have a regression model with just an intercept, we say 1. So let's just have a summary of the base model. And there we go. We just have the intercept. We have nothing else. So it's just basically a mean value. And now we're going to have the full model, which is basically everything but the kitchen sink in there. But it probably, again, has it's probably overfit. It probably has too much information to be useful. You see we have, and some of these NAs just means there's not enough information for the individual class to specify the model. But you see we have a lot of variables. Some of these are significant. Some of these are completely insignificant. So what do? Well, we can do stepwise regression. What it does is a forward stepwise regression starts off the base model, and then it basically will say, okay, we're going to add the variable that gives the biggest improvement in, like, the R squared. Then we're going to do it again, and then we're going to do it again. And we're going to carry on until the model gets no better. How do we determine if the model gets no better? Well, we can use some variable of fit that accounts for the number of variables. We can use the adjusted R squared, or we can use something called the AIC. It's a little bit beyond this class, but it's the Akiki information criteria. It's just kind of a measure of how good the model is, but accounting for the number of variables. So let's just kind of, we've got the base model, we've got the full model. So what we do, we run step, base model. We've got the scope command, and this just tells us we're going from the base model to the full model. And we're going forward, which means we're going from the base to the full. And so I'll run this, and this will take a few minutes, so I'll just pause the video. Okay, so it actually stopped running. And you can see here it's using, I said, the AIC. This is just, the regression function has something called a statistical likelihood. And the AIC is based on that. But all you really need to know is kind of the lower the AIC, the kind of the better the kind of the model fit. So you can see here that as we started off with a much higher AIC, and we kind of carry on adding variables until we kind of get no lower. And we can actually do kind of a summary on what we have in our final model. And here we go. This is our final model with all of our things. Now you see most of these categories, at least one of the category members is significant. The thing is here is that you can't, like, if you have a qualitative variable, a categorical variable, you've got to kind of include all the relevant dummy variables or none of the relevant dummy variables. So if one's significant, then you basically throw everything into the model. So you say, for example, here the basement, we have quality excellent is mildly significant, and then we have basement exposure, good is mildly significant. Again, we have all our neighborhoods, and we have the overall quality, and the living area is very significant. So we've actually built our predictive regression model now. And if we had a new house that came on the market, or if we had an assessor working for the government, we could put all this information in, and we could get some kind of prediction of the overall house price.